So today we're going to talk about finding the area between two curves. Now we've already talked about area and integrals before, and we said if I had an integral, one interpretation of that integral is that this represents the area between v of t and the x-axis on the interval from 0 to 3. And the first way we talked about that is that you can estimate that area using a whole bunch of rectangles added together, which will get you the area between the curve and the x-axis. Well, today we're going to talk about finding the area between two curves. So instead of one curve in the x-axis, we have one curve and another curve, and we're going to find the area all between that. Now, what's important to note here is that the word area really implies that you're talking about a positive value. So if I want all of this area to be positive, what I want to make sure is that I consider each of these rectangles to have a bunch of positive area inside of it. Now you might be thinking to yourself, wait a minute. When we did this before, the area above the x-axis was considered positive and below the x-axis is considered negative when you use an integral. Well, this isn't going to be a problem in this case because what we're going to do is to find this area, we are going to break this up into a whole bunch of representative rectangles that look like that, which are shown over here on this side, okay? Well, if I want to find the area of a rectangle and add all those rectangles together, I would have to figure out the length of each rectangle and the width of each rectangle. Well, the width is going to stay consistent from what we looked at before. My width is going to be dx. The height of my rectangle is really just going to be the distance between 2 points on the top curve and then on the bottom curve. Well, let's say if I look at this rectangle over here, and I say, well, that top height has a y value of 4, and this bottom height has a y value of -2, that means the height total is going to have 6 units. Well, how did I get 6? I simply took the difference of f of x and g of x. I took the difference of their y values, and that gave me the height of the rectangle. So really, long story short, when you want the area between two curves, you're using two representative rectangles, finding the difference between them and adding them up. Well, adding them up speaks to the integral. A and b represent your boundaries, and f of x and g of x are your two functions where f is above g, which is why f comes first and g comes second. So what's important to note is when you deal with this integral and you set it up for yourself, the first curve you write needs to make sure it's the top curve, and the second curve that you write has to be your bottom curve. Now, if f and g cross each other, and instead of f always being above g, f and g crisscross at some point, maybe they look something like this. And I have, let's say right here, this is going to be f of x and this is going to be g of x. And let's say they cross at 0, 3, and I don't know, let's say 5. On this region right here, if I look, f is on top and g is on the bottom. So this would be the integral from 0 to 3 of f minus g. But on this region over here, g is on top and f is on the bottom. So for that one, I'd need to do the integral of g minus f from 3 to 5. Add those together and you would get the total area of my shaded region here and the dotted region over there. So now let's look at a couple specific examples over here. So if I want to find the area between the curve of y equals secant x and y equals sine x on the interval from 0 to pi over 4, I'm really looking at this region right here. So if I want to find the area of that region right there, I'm just going to follow the rule that we just talked about. And that rule being that I would take the integral of the top curve, secant squared x, and the bottom curve, sine x, on the interval in question, which is 0 to pi over 4. So if I want to evaluate this integral and they're telling me I'm not supposed to use my calculator, I'm going to have to integrate it by hand. When I integrate by hand, the antiderivative of secant squared is tangent. The antiderivative of negative sine is actually going to be positive cosine. from 0 to pi over 4. Now I'm going to plug in my bounds and subtract. So I have tan pi over 4 plus cosine pi over 4 minus tan of 0 minus cosine of 0. So this is going to be 1 plus root 2 over 2 minus 0 minus 1. And actually, this is supposed to be a plus. My apologies. So then when we go to evaluate this, I have 1 plus root 2 over 2 minus 1, which gives me a net value of root 2 over 2, meaning this region right here has an area of root 2 over 2. And that's all you have to do. Area between two curves, you take the integral of the top curve minus the bottom curve on the interval in question. If you've done that, you have the resulting area. So let's look at another one. Still no calculator down here. Find the area enclosed by f of x equals x squared, g of x is 9, x is negative 1, x is negative 2. Sketch it first. There's a lot of stuff going on there, and the only way to get through it is to draw a sketch. And you should be able to draw a sketch of something like this by hand. So I'm going to draw x squared. Again, a sketch will do here. Here's f, and then g is 9. So that's the line y equals 9. And if I think about x squared and 9, they are going to intersect when x equals 3 and negative 3. So now I know that when I draw negative 1 and 2, they're going to look like this. And I want to find the area enclosed by all that stuff. So it basically means find a bubble where the four sides of the bubble come from those four functions. And that's this shaded region here. So if I want to find the area of that shaded region, one of the things that sometimes I'll do is I'll draw in my representative rectangle just to give me an idea of what I'm looking at here. So if I want to find the area of that representative rectangle, I have to do top minus bottom to get the height. The top is g, which is 9. The bottom is x squared. And I'm shading from x equals negative 1 to 2. No calculator? That's fine. We can take the antiderivative by hand again. 9x minus 1/3 x cubed from negative 1 to 2 is going to give me 18 minus 8/3 when I plug in 2, minus negative 9 plus 1/3 when I plug that in. So 18 technically plus 9 is 27. Negative 8/3 minus 1/3 is going to be minus 9/3, which is 3. 27 minus 3 is 24. Same thing as before. Area is top curve minus bottom curve. Evaluate the integral. All right, so now one more without our calculator here. Find the area enclosed by another parabola, and this time a slanty line. Not a big deal. So if I want to draw the graph of negative x squared plus 2, that's going to be an upside down parabola with its vertex at 2 up here. And then if I draw y equals negative x, it's going to come through the origin and look something like that. And this is h equals negative x squared plus 2. Again, we see this phrase enclosed by. So enclosed by means find the bubble created by those two functions, and it's right there. So if I want to find the area of that region, I'm just going to take the integral of the top curve, which is the parabola, minus the bottom curve, which is y equals negative x. Except the problem being this time, I don't have bounds. Well, my bounds would just be where they intersect, which would be right here, we'll call that A, and right here, we'll call it B. Well, how do I figure out where two graphs intersect? Just like you did when you took algebra years ago, you say, well, two things intersect when the equations are equal to each other. So off to the side here, I just want to know when negative x squared plus 2 equals negative x. So 0 equals x squared minus x minus 2. And I'll have x plus 1, x minus 2. So x equals negative 1 and 2 are my values for A and for B. Well, that just means that the boundaries of my integral are negative 1 and 2. And then from there, it's just integration techniques. So I want to take the antiderivative, negative 1/3 x cubed plus 2x plus 1/2 x squared from negative 1 to 2. If I plug in 2, I'm going to have negative 8/3 plus 4 plus 2. When I plug in negative 1, I'm going to have, let's see, a positive 1/3 minus 2 plus 1/2. And then if I evaluate all of this, trust me on this, I'm going to end up with 9/2. And that's just arithmetic. You can check it on your calculator if you'd like. But that ends up being 9/2. And there's the area of my region. Now, when we look at number 4, a couple things stand out. I've italicized the word total. And there's probably a reason for that. And it also says use the calculator. But be sure to write out all your integrals used. So the first thing I want you to do at home is look at your calculator, and I want you to graph these two functions on your calculator. If I wanted to graph them myself, my smartboard could probably do that for me, but I'm just going to draw it for you. So while you're graphing on your calculator, I'm going to be graphing up here on the screen, and you should see something that has a nice happy cubic function like this. And this is y equals x cubed minus 4x. And then a very shallow slanty line that looks something like that. Y equals negative 0.1x. And it says I want the total area enclosed by. So the word total gives me the idea that there's probably more than one area. And enclosed again means that I want to look for bubbles. Well, there's actually 2 bubbles this time. There's the bubble over here, and then there's the bubble over there. And I want to figure out what that total area is. So this is a case where the graphs cross each other somewhere in between the endpoints. So they crisscross right here. Now they're going to crisscross at the origin. That's something that you can figure out on your calculator as well. I didn't want that. That meant to be an O. Their origin is right there, and that's where they cross. So that means I need to separate my integrals at the origin. So I'm going to start writing out integrals here. I have the integral from whatever this value is, I don't know what, down to the origin. So from something to 0 of the cubic minus the line. So the cubic minus the line. Then to that, I need to add the integral from the origin to another value that I don't yet know. And this time, the top line is going to be the line, and the bottom is the curve. So I have negative 0.1x minus the quantity x cubed minus 4x. And parentheses are incredibly important there because you want to make sure you're subtracting the entire function. Now, just like before, I have a problem because I'm missing some boundaries here. But you have a calculator. I'm telling you to use it. So you're going to hit second calc intersect, find these 2 values, and you're going to find values of plus and minus 1.974842. One of the things you can do is in your calculator you can store these values. Let's say a equals the positive 1.975-ish and b equals the negative 1.975-ish. And when you write out your integrals, you could even identify these values and then within your interval put a B there and an A there as long as it's been identified elsewhere. And then when you type it in your calculator, you have those stored values. Now again, now that I've set up my integral, I don't need to integrate by hand anymore because I'm telling you to use the calculator. So in your calculator, you're just going to plug these 2 integrals in. This first one is going to give you an area of 3.8025. And the second one is as well, because actually both of those functions are odd, so their areas match up, which gives me a final answer of 7.605. And again, I didn't do this by magic. I put it into the calculator, and it gave me a response. So far, so good. Moving on. All right, so we're 14 minutes in, and we've already done a bunch of different types, so the next one should go a little bit quicker here. Find the area in the first quadrant bound above by y equals the square root of x, and below by x minus 2. Sketch the area first. You may use your calculator. All right, so fantastic. I get to use my calculator. So you graph it on your paper. I'm going to quickly graph it up here. Here's y equals root x. Here's y equals x minus 2. Again, this is a rough sketch here. And it says find the area in the first quadrant. And actually, square root of x really shouldn't have this little tail on it. I'm going to erase that. So I want the area in the first quadrant, which means really I just want this region. Now I'm going to draw representative rectangles again this time, because if I draw in my rectangle, right here, my rectangle is bound above and below by the curve and the line, but over here, this other rectangle is bound by the curve and the x-axis, which means I need to have two integrals, because technically my region is separated by the square root of x and the x-axis, and then over here by the square root of x and the line x minus 2. So for consistency's sake, I'm going to use red for this integral. Well, this integral would be the integral from the square root of x to the x-axis. Well, the equation to the x-axis is y equals 0. So technically I could put square root of x minus 0, but that's just silly. No one does that. So I just need the square root of x dx from 0 till, okay, from 0 to where this crosses the x-axis. Well, y equals x minus 2 would cross the x-axis at 2. So there's my first integral. And then my second integral is going to be the integral from the square root of x down to x minus 2. And again, my parentheses are important. And so if I have that all set up, let's see, that's going to go from 2 to where these two things intersect. So if you have your calculator, you can do second calc intersect, find out where they cross. And trust me on this, they are going to cross at 4. So I'm going to put 4 up here. Now that I have everything set up, you're going to throw it into your calculator. Integrate this, integrate that. The calculator is going to tell you 1.886 and 1.448 for a grand total of 3.333 for your area. All right, I am going to pause here. That way this file doesn't take too long to load. Come back for part 2 in a minute.